Right. Hello, everyone. Good afternoon. So this is Vishnu Balraj from Micron. I'm part of the product management team. So it's going to be exciting today. We'll talk about how to enhance AI and database performance using CXL devices.
It was because of your new label. I didn't
Yeah, this is a new Micron label. Yeah. So we'll see how to specifically the focus is going to be on the CMMs, CXL memory modules is what we're going to talk about. So let's look at the high-level data center challenges what we have today. And most of you know about the memory and storage hierarchy. So I'll just call out so that you have a context of it. And following that, so Micron has two CMM products. So one is CZ120 that we have already released and it's in production. So the other one is CZ122. We'll talk about it. And then the exciting part of this presentation is going to be we'll talk about the use cases and we have some demo booth also outside. So we have internally vetted it and it's been kind of be working with many partners on this. So we'll talk about it. And then finally, how to enable CXL in your company. So those are the topics. So just to touch upon the data center challenges, so in-memory database, SAS, and then AI, specifically RAG, right? We'll talk about the RAG. So we'll be curious about how CXL plays in AI. So I'll be emphasizing on usage model on specifically on the retrieval augmented generation. So these things requires more capacity. So this is one of the major challenge actually. As the compute grows, the memory capacity also grows. The database requires a lot more capacity. That's one of the challenge. And the second one is, so you know that last week AMD released Turin processor. So the core count is tops at 196 cores. So these compute requires more bandwidth. And how do you address the bandwidth of the additional compute need? And in the same time, these workloads require to be optimized for the TCO. They demand higher bandwidth and capacity. So how do you ensure that we optimize the TCO using CXL actually? How can we overcome these challenges using CXL? So if you look at it, this is the memory storage hierarchy, storage hierarchy. All of you know about it. So as you go up towards the HBM, you're going to get lots of bandwidth. And as you go down, there's going to be an increase in latency and increase in capacity also. So CXL sits kind of in the sweet spot actually where you can get the best capacity expansion and then the bandwidth expansion. So we'll see how to achieve that. So the first one here, so CZ120. So this is the product. This is in production now. So this is a CMM E3.S 2T form factor. It's a CMM module. You can plug in. Later on, I'll show that we have worked with SMC, so it can be plugged in on a server. So we are offering 128 and 256 GB capacity, and this is based on CXL 2.0 specification. So we are offering the industry-leading low latency and high memory bandwidth. We top at 37 GB per second. And this is again on the CMM category with the PCIe Gen 5 by 8 lanes is what you're talking about. And the way we measured this was through MLC, benchmark 2 read, 1 write. So this is where most of the workloads require 70-30, and we are able to demonstrate that. So this is a standard E3.S 2T form factor. So this is already in production, so you'll be able to get it. It's already launched and in production. So the second product, what we have here is the CZ122. So this is, QS is already done and we are sampling it. So this product will be available soon. So the difference between the CZ120 and 122 is that this one has hetero interleaving support as well as metadata support. So some major platform vendors require metadata. With metadata, you can do the hetero interleaving. So a lot of them talked about the heterogeneous interleaving earlier. So what you're talking about is hardware-based heterogeneous interleaving. So with the CZ122, we'll be able to enable the hardware-based hetero interleaving for all major CPU platforms. From the usage model standpoint, what does it give? So you can just plug in, and then you can get both capacity and bandwidth expansion without any software-based tiering or anything. That software-based tiering can still be done, but you can get both bandwidth and capacity just out of the box. And that's the main advantage of CZ122. And in addition to that, we have the RAS capability, what I've talked about here. So in terms of RAS, we can talk about for the features that we are supporting on RAS for CZ122. I'll just call out a couple of them. So one is the internal CVMe threshold that we support. So where you can program your memory threshold, and once you hit the number of memory errors, it automatically sends a notification back to the OS for doing the page offlining. And this is more of a OS feature, and then we built it in the device to make sure that it seamlessly works with that. And the second one is the device initiated PPR, HPPR. So when the device boots, so we'll enable the hardware-based PPR, right? So it'll fix if there are any memory errors. So those are the two features we are offering in CZ122 actually. So that is in QS done, and it'll be in production soon. So we'll keep you posted on that. All right, so this one got a little messed up here. Okay, so I'm going to talk about the scale up with CXL. So I do have the picture here. This is something that we have collaborated with AMD and SMC Supermicro. So what we have done here is, so if you take a baseline today with 128 GB RDIMMs, so you can only run certain number of VMs. So by being able to add additional CXL modules, you can run more number of VMs, right? So that's what we are trying to demonstrate. As the number of cores increases, you can get utilization of a processor by adding CXL, because some of these database workloads require more memory. Right, apologies for this blank here, actually, I need to check. And so the second one here we are talking about is RocksDB performance. So this one we have worked with H3 platform on this one. So we are introducing a concept called Famfs. So this one, I think it's probably CXL 2.0 is the first time we are enabling the sharing model with the CXL. So I'm going to show how we can use Famfs to enhance sharing using the CXL and improve the overall system performance. And the third one is the RAG actually. So this is everyone knows about RAG actually. So RAG stands for Retrieval Augmented Generation. So via CXL, you can improve the overall time to first token, as well as you can also improve the overall latency of a RAG plus LLM system, right? So that's what I'm going to talk about later. And this is something that we're working with the Memerge on this one. So the first use case, let's look at this, right? So in this, if you look at it, so the VMs are running so in a direct attach mode, right? So this is the baseline what you're talking about here. So we're able to run, so using TPCH as a benchmark, we're able to fire up around 45 cores or so. So each of the TPCH requires around 34 GB or so. And we had, on the direct attach, we had about, it's a 12 channel, so 128 GB and 1.5 terabyte total. So, so immediately it kind of ran out of it because the number of cores are so high and it needed more memory to have good enough performance. And so the DRAM is called out as a NUMA 0, so it's the baseline, and then the CXL is in a NUMA 1. So what happens, right, if you look at on the right hand side, the graph here, so with the DRAM, you are able to do the scale up factor up to 1. Let's say, so many VMs are fired up and it's all running. So using CXL, you are able to increase the overall utilization, the memory utilization, up to 70%, right, with the CXL plus DRAM. So what you have, 1.7x is what you're able to improve it. But now one can ask, so what happens to the overall performance because the CXL is a low latency? But what we have seen in this benchmark is the purple line you're seeing here, the gray line you're seeing here is with the DRAM, and this purple line is with CXL, when CXL is added. So if you look at the overall performance, when you added that additional VMs, right, up to 70%, your average performance is only gone down by only 6%. So CXL latency has not impacted the performance, and overall bandwidth kind of counts in this. Only certain bandwidth counts, and CXL is able to provide that. So that's the point number one. We are able to increase the up to 70%. And the second point is I want to bring up is, so this is a scale up actually. So what can one do, if they want to run more number of VMs, and each of the VMs, if they want to run database or data-centric workloads, they can either add a new system or they can scale up using CXL. So in this model, so with the current price point, we are able to, by increasing the CXL, we added up to 1 terabyte of capacity, 256 GB. by being able to add it, your price performance per dollar, right, goes up by 1.2x. If you assume the baseline server is a 1. So you can push the CXL by adding more CXL, you will be able to push it up. In some servers, you can add up to 8 CXL devices. So you get more memory and you get more performance. And that's one way to scale up the performance without adding a new server. Okay, so this is one usage model. And so this talks about, what server we used here. So if you look at it, on the bottom here, you see this is the Supermicro H13 petascale storage server. So it has got the CXL slots in the front. You can put up to 4 CXL slots. This is the storage server. So this is where the evaluation was done. Yeah. And so I'll go to the next one. So this is a RocksDB. So if you look at the left hand side, right? So this is how traditionally the RocksDB has been run. So you have storage, so where you're putting the database, and now you have these 2 VMs running on it. The same database is being read by the RocksDB application. What happens is, in this case, the VM1 and VM2 are having, this is a local attached DRAM. So they're having duplicate copies of the same database. So this is traditionally how it was done, and this is a DRAM only system. And in this system, we have CXL. So in this, DRAM is there, but DRAM is not used in the sense I'll explain it. So what we are doing is, Micron is introducing a concept called Famfs. So Famfs stands for Fabric Attached Memory File System. So the idea is, your DAX concept, right? DAX concept, direct access to the memory. So the application can directly access to the memory. Taking the DAX concept and then file sharing, both are merged into something called Famfs. So that way, each of these applications the entire database is loaded on CXL modules. It makes one total of 1 terabyte here. And each of these databases, right, this is again read only. It's not a read write, it's a read only. So they're able to avail this directly without going and buffering in the local DRAM. So with that, right, you are able to get much better performance actually when the databases are large. And then the other important point on this, there is no this is deduplication done. So by that also you are able to save. And this we have demonstrated with 4CXL E3.S in a server. So one can also enable this with multiple nodes, where you can have a switch and you can have the CXL 2.0 devices up to 5.5 terabyte, and then you can share it in the multiple nodes. So that's another huge advantage. So I'm going to show you the benchmarks that we have done, right? So this Famfs is something that Micron has taken the leadership on, and we have pushed the patches in the kernel, and our engineers are working on it. And in about, I cannot tell the exact timeline, but in the future, we will have a kernel available with the Famfs for all the customers. Our customers can use this. So here I will show you the results of the benchmark that we have done. So on the top, you see this is the operation per second. This is the overall performance that we are looking at. So the orange line that you are looking at, that's the DRAM plus SSD, right? So the x-axis here is the DB size divided by DRAM size. So what we have done is we have taken the DB size and database size, and we have increased it with the first system. So the performance is really good. The ops per second is really good. And then what happens suddenly, it goes for a toss when the database size goes beyond the DRAM size, because your DRAM size is small enough because you are duplicating it. It's used as a cache, and then it goes to the storage. So it really lowers. But what we have found interesting is the blue line you are seeing is 2 CXL cards, and the performance is low. And the yellow line that you are looking at is the Famfs with 4 CXL card. The Famfs with 4 CXL card performance is equivalent to what you have in DRAM in terms of the operation per second. And since it's all sit in a single CXL shared memory, you can increase the DRAM size, and you're able to get the same performance, sustained performance over the period of time, right? And here again, in this case, there's a P99 latency. By the way, this is a logarithmic graph. So initially, DRAM latencies are better in the first few database when the database size is really low, because DRAM is faster. But as it goes along, when you increase the database size, again this logarithmic scale, right? This P99 latency goes for a toss for a DRAM, but your CXL is exactly consistent. So this is the best part where you're not actually doing a buffer copy also. So therefore, everything is sitting on CXL and many different DBs, RocksDB applications is able to use it. This does not require any changes to be done on the RocksDB also, so it can be just working. And there is also deduplication saves overall system power. We haven't quantified that, but there are a lot of benefits, and this is possible today, right? With the direct attach as well as with the multiple nodes. So here we have collaborated with H3 platform, and so like what I said is, it's a 1 terabyte total, and this one goes up to 5.5 terabyte overall. You can take 256 GB, and you can attach to, with a switch, you can attach to many nodes, and many nodes can use the same database. And so this is the last but not least, actually, I'm going to talk about this usage model here. So RAG stands for Retrieval Augmented Generation. So this is becoming more prevalent in enterprises. So the idea here is, with LLM being trained sometime, like last year or last couple of years ago, everyone wants to always have the latest and greatest data, right? So RAG is useful on that one scenario. The second one RAG is being used is enterprises have their own data sets, and they want to take the data set and put it in a RAG system, and they want to do a similarity search and add additional context. And the additional context is given to this LLM, and LLM is able to take it, and then it's able to generate the new answers. So this LLM is running on, let's assume this is running on a GPU, right? So what we are talking about here is, how can CXL help with the RAG pipeline? Because overall the performance of this is going to be measured by TTFT, right? That's one of the performance metric that is being measured, which stands for total time taken for the first token. And the second one is the total latency. So if your RAG latency increases, your TTFT and the overall latency is going to increase. So it's important to optimize this RAG. So that's the point one. So now this RAG is today being run on CPUs. The reason is it's not compute intensive. So with that, right, with the CPU, we already have CXL. And like whatever the challenges that I said earlier, RAG requires large databases, because we are talking about vector database here. So we are taking the existing data set and converting into embeddings and then indexes. It kind of blows up in the size. So we have seen, some of our internal analysis indicate, that this size could be going up to 6 terabytes or 8 terabytes. So these are all sitting in the storage. The more you push it into the CXL, it's going to have better performance. And so that's how what you do is, you're able to reduce this overall latency on this overall, when the user query gives, with the retrieval search, this is going to add latency. So when you add more latency to that, the user gets impatient, right? So this is where, we are looking at adding CXL and improving the overall performance, AI performance. And then this part of it, it's still on HPM, and we will look at it in the overall GPU, right? But this RAG part is what we are talking about here. So again, this one we haven't quantified the exact results of how much it improves. So we are planning to put together the data. We are working on it, and hopefully by supercompute we'll be able to share some results. But this is another real strong use case where we think our CZ122 Micron modules will be able to improve the AI inference latency and the response time while using RAG. All right, so okay, so now actually this is more of a call to action. So if you're further interested in Micron CXL devices, CZ122, so we have a website, micron.com/CXL, and we have a program called TEP program, Technology Enablement Program. So we would suggest you to sign up for that, and we'll get you the support, and we'll be able to get you the collaterals and the data sheets and all that good stuff, and we'll work with you to enable CXL in your company. So that's all I have actually. Almost 20 minutes. Any questions? Can I take any questions?
Unfortunately, no.
No,
Because
okay.
they're running us out of here. So
okay, thank you.
Thank you, Vishnu. And also thank you for being co-sponsoring this event.